Okay, today we're going to be going over a practice final exam. Our first problem here is a basic PMOS amplifier with a current mirror source. So first we want to find out, first question is, what is the DC voltage at node A? And we know that node A here is tying together VG and VD of NMOS 3 here. And we're given V over equals 0.2 volts and V threshold equals 0.8 volts for VTN. And so what we're going to do for part A here is we know that VGS equals VTN plus V over. So therefore, that equals 1 volt. So VA equals 1 volt because source is ground here, so VGS is VA. So that's part A. Part B wants to know what the widths of Q2 and Q3 are. So what we're going to do here is these are in saturation. So we're going to use the saturation equation, ID equals 1/2 Kn prime times W over L times V over squared. You can put in the 1 plus lambda if you want. You don't need to. It's up to you. And then we're going to rearrange this to solve for W. So we get W equals ID times L times 2 over Kn prime V over squared. We know that ID equals 50 microamps. L equals 1 micrometer. Kn prime equals 120 microamps per volt squared, and V over equals 0.2 squared. So that gives us W of 20.8 micrometers. And W3 equals W2, it's W, because they're 1-to-1 current mirrors. So both of them equal 20.8 micrometers. If you include this 1 plus lambda, lambda is just 0.1. So it's just divide this 20.8 by 1.1 and you'll get a width of 18.9 micrometers. Now for question C, it wants us to draw the small circuit analysis of this, just using this circuit mirror as a resistive load. So we're going to have our gate, our source, our GM1, VGS1. This is our V out here. This is drain, this is source. VN, oops, excuse me. VN is over here. Source is also at ground. I'm going to have R01 and R02. So we got our GM from 1 from right here, this transistor. We have our R01 from this transistor, and then we have an R02 from this transistor, which just goes from out to ground, and you see this goes from out to ground. So that's how we're just treating this R02 as a load resistor, essentially. Is all that's coming from this transistor down there. And so that's all we need for C. For D, we want the small signal voltage gain. So in order to do that, our VGS 1 equals V in, our V out equals negative GM 1 times V in times R out 1 times R out 2 over R out 1 plus R out 2. This is just these two in parallel. It's just current times resistance equals voltage. Bring this voltage over, and you get AV equals V out over V in equals negative GM1 R out 1 R out 2 over R out 1 plus R out 2. And we want to numerically solve for this too. And you notice that this R out 1 times R out 2 over R out 1 plus R out 2 is just the total output resistance. So now we need to find R outs and GMs. R out, the equation for R out is 1 over lambda ID. Lambda is the same for both of them. It's 0.1 for both. And ID is 50 microamps because the current mirror is 1-to-1 and our current source is 50 microamps. So that gives us a resistance of 200 kiloohms. And GM is equal to 2ID over V over. V over is 0.2 volts. So that gives us a GM of 5 times 10 to the negative 4 siemens. And that gives us an AV of negative 50 volts per volt. Now, part E is how does the voltage gain change if you double the current while holding V over and L constant? Well, let's take this equation and plug in these for this. And so we'll get AV equals negative 2ID over V over times 1 over lambda squared ID squared, which is just, these are the same because lambda and ID are the same for both, times this is lambda ID over 2. I'm just 1 plus lambda ID plus 1 plus lambda ID is 2 over lambda ID. It's 1 over that, so it's lambda ID over 2. And so that all these IDs cancel, the 2's cancel, and you get negative 1 over V over lambda. And this lambda is a function of length, and length is constant and V over is constant, so AV is constant. You see your AV is not a function of I, so AV does not change. With I bias with your current. So the current is just to bias everything into saturation. It doesn't actually change your gain. Now we're going to go on to problem 3. So part A of problem 3 says, considering the circuit in figure 2A, we can simplify our frequency response analysis by evaluating the current mirror as a standalone circuit. Therefore, draw the high frequency small signal model of only the current mirror. Include only gate to source capacitances, ignore all other capacitances. So now we're going to do the high frequency model for just the current mirror. So that means we're just looking at these two transistors. And I'm gonna redraw them over here. Okay, so let's do for 3 here. So we have our drain is here. Our source is here. Our source is just ground. This is R0 3. We have a current here. It's GM V GS3. This comes over to the gate over here. And you notice that I tied the gate and the drain together because it's tied together on the circuit. This is the gate G. This has CGS3. And I'm tying the sources of these together because they're both tied to ground. And the gates are tied together, so let's go over to this gate, G. And this is VGS3 right here. Is across this, which is equal to VGS2. So this is CGS2, and then we get our GM VGS2 here, and we get our R out 2 over here. This is V out right here. So there's that. Part B wants us to mark any node pole associations and say how many poles are associated with it. There is one pole on this right here. Pole. This is where we have capacitors and resistors are all tied into this. So we have one pole. For part C, we have already analyzed the current mirror, so now we're just going to use it as a resistance to our transistor Q1, and we want to find the dominant pole of the amplifier. So remember, we're just hooked up over here. And VGS is 0. So what we're going to see is we're going to have our VN. Remember, this is for 1 now. This is for the amplifier. We don't have any R sig, so we don't have a pole over here. So the dominant pole here is the only pole that's in this, which is right here, right around V out. So that's going to be WP is going to be 1 over R out C out, which R out is these two in parallel, which we already know. Is this, and so there is our WP. So D asks, what is the approximate numerical value of this? And we already know that these are 200 kilo ohm resistors, so two 200 kilo ohm resistors in parallel. 100 kilo ohm is a 100 kilo ohm resistor, and CL is 10 picofarads. Let's write this down. R out is 100 kilo ohms. And that means our WP is 1 megarad per second. So that's our dominant pole. And that's all there is for 3. You can see here from this analysis that this pole doesn't affect this at all. There's nothing small signal going on in this current mirror. If there is a CDS over here, on this side, then we care. But since all the capacitances are on the gates, it doesn't, you don't see it show up anywhere here. Like this resistor adds to the resistance, and I mean it's in parallel, so it actually makes the resistance less. But this resistor shows up here, but there's no capacitor over here, so we don't care about this pole at all. So now I'm going to go through a couple of digital problems. And we're going to call this 4-1 because there's actually 2 problem 4s. So part A is to implement y equals a plus bc. And I like to do pull down first because that's easier. So let's list that as y naught equals a plus bc. So we have our y here. We have a here. And I'm going to use digital notation for these transistors because it's a digital circuit. You can use analog source if you want, as long as grader knows what you're saying, you're fine. So I just did A, or B, and C, and that's the pull down network. And so let's flip that into the pull up network. So this is A, or B, and C. And so that's part A. I find it easier to get it in a y naught form and do the pull down first, because if you do that, it's A, ORs are parallel and ANDs are series, which I find easier to remember. If you do the Y version, you have to remember that these are all knotted. And I find it easier just to do the pull down. It's up to you. If you get the right answer, you get the right answer. And there's a bunch of different ways to do it. I find this the easiest way. Okay, now for part B. So we have y equals AC plus BC naught. And so this way, it's kind of a pain to get the pull down network first. There's no easy way to get the pull down network first, so we're gonna have to do the pull up network first. Luckily, this is a pretty easy pull up network. So I'm gonna have A, C. Remember, this is pull up, so they're knotted. Let's C, B, not. And so if A is 1, then this is on. And if C is 1, this is on. And that means we're connecting high VCC to Y, which makes Y go to 1, which is what we want. And now we're just going to transpose that. Needs A naught, C naught, in parallel with, or in series with the parallel C. And so that's that for B. There are other ways to do this that will get you the same answer. You can split these up into 3 different series, so you don't have any parallelism here. But the reasoning behind that is you go over in digital circuit design, so you don't have to worry about that here. So now we're going to do 4.2. 4.2a gives us this circuit. And wants us to make a truth table. So we can derive it right here. Some of you might know this. It's a pretty common circuit. If A is 0, let's assume for now that Q naught is 0. That means Q is 1. If Q is 1 and B is 0, that means Q naught is 1. We assumed Q naught was 0, so Q naught being 1 is impossible. So let's assume Q naught is 1, and you see that doesn't actually change anything because A is 0. So these two have to be DNE. Sorry, if we assume Q naught is 1 and A is 0, Q is 1, and that goes through, and this is, yeah, you can't have Q and Q naught be the same thing. They have to be the opposite of each other. So these are DNE. You can't have 0 and 0 coming in here and getting actual values out of these. If we put in A equals 0 and B equals 1, and we assume Q naught is 0, that gives us a 0 out here. Gives us a Q of equal to 1. Bring that over here. B is 1, Q is 1. Q naught has to be 0. That works because those are complementary. If A is 1, and we assume Q naught is 1. If A is 1 and Q naught is 1, Q would have to be 0. Q being 0 and B being 0 gives us a Q naught of 1. Which is what we assumed it to be. Now if A is 1 and B is 1, Q is just knotted Q naught, which means it's just Q. So it's Q previous. And Q naught is just knotted Q, which means it's Q naught previous. So all we have here is A is 0, B is 1 is a set. A is 1, B is 0 is a clear. And then if they're both 1, it's a store. So this is a type of latch. For B, and C, we're considering this circuit. And so C wants us to draw the pull-down network, so let's do that first. Oops, this is D. So the pull-down network for this is D is going to be in parallel with A, which is in series with B. C. So this part's actually C. B is asking us what function does the circuit implement. C is asking us to sketch the pull-down network. So here's the pull-down network. You can get the function from the pull-up or the pull-down network. Once again, I like to go from the pull-down network. It's just easier for me. It's totally up to you. So why not equals D or A and B or C. If you got it from the pull-up network, you would do Y equals D naught and A naught or B naught and C naught. I like to do pull-down network because these are the same as the inputs instead of inverting it, which you have to do for the pull-up network. Okay, there we go. That was 4 problems from the practice final. You got some small signal analysis, low frequency analysis, I should say. You have some high frequency analysis, and you have some digital circuit analysis.